Um, so we're going to start with a way to generate polynomials. So we're not generating a series quite yet, but we're gonna generate polynomials with a various number of terms. So the idea is that we want a procedure to approximate functions with polynomials. Why would we want to approximate functions with polynomials? Any ideas? Yeah?
They can be easier to deal with the function itself because you can just use an appropriate number of terms as accurate as you care to go.
Right. So we can the polynomials are nice. They're easy to work with. Their derivatives are nice. They're friendly functions. So a polynomial may be easier to work with than some other function that you're trying to approximate. And the approximation that gives us a way to say, okay, we want to approximate to a certain degree of accuracy. So we're just going to use 5 terms of this polynomial, something like that. And polynomials involve multiplication and addition, which is what computers are good at. Other functions for computers to work with other functions, the computer doesn't know what e to the x is. But if you tell it it's x plus x squared over 2 plus x squared over, the computer can do that. So that's one reason why we might want to do this. We're going to call our polynomial, in this case, p of x for polynomial. And what we want to do is we're going to begin by picking a point in the domain of our function. So we want to approximate these functions around some point, around x equals 5, for example. And we're going to say that the polynomial, our terminology, is expanded about C, or centered at C. So we're going to approximate our function around some other point. And later on, we're going to be interested in, well, if we use this as an approximation, if we use the series as an approximation, when does it converge? And it's nice when you have a large interval in the domain of the function where your series converges. It's especially nice when it converges from negative infinity to positive infinity. All right, so for Taylor polynomials, our process is we want the function and the polynomial to agree at C. So we want P of C equal to our function value there. So what we're doing is we're saying, okay, we want to know where something is. We want to approximate where it is after a certain amount of time. Well, the first good guess is where it was the last time you saw it. We're going to make the approximation more accurate, so for more accuracy, we're going to make the derivatives agree. So we're going to require P prime at C equal to F prime at C. So we want the first derivatives to agree. So now if we want to figure out where something is, we talk about where it was and how fast it was going, for example. And then we continue requiring the higher order derivatives to agree. So we want P double prime at C equal to F double prime at C, the third derivatives, etc. And we can continue and require as many derivatives to agree as we want. And that's how we're going to build up our polynomial. So this is how we're going to construct our tailored polynomials, where we're going to require that the functions and the derivatives agree for however many derivatives we're going to take. All right, so we're good there. All right, so let's write out our polynomial. So we're going to say P sub n, for however many n terms that we're going to have, is a0 plus a1 x minus c. So we're centered at c here, plus a2 times x minus c squared, plus a3 x minus c to the third, plus dot dot dot, plus a to the n x minus c to the n power. And this is going to be our polynomial expanded about c. And the a1, a0, a1, a2, a3, we need to determine. So we need to determine those constants so that this polynomial satisfies our requirements for our approximation. Well, let's look at what happens when we start taking derivatives. P prime of x is a1, because this is a constant, a1 plus 2a2 x minus c plus 3a3 x minus c squared plus dot 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 plus n, when we take the derivative here, a sub n x minus c to the n minus 1. And we're going to take a derivative again, p double prime. Well, this time a1 goes away and I get 2a2 plus 2 times 3 here, a3 x minus c plus dot dot dot, and I get plus n times n minus 1 x minus c to the n minus 2. And I'll write out one more. So we want to see the pattern here, and then we're going to start substituting our points in where we're expanding. Yeah.
So in the our P double prime, is it n times n minus 1 times a sub n times?
Oh yes, I forgot my a sub n. Thank you. So my third derivative, now when I take another derivative, this is constant, and I get 2 times 3 a sub 3 plus, and I'm not going to write out all the in-between terms, plus n times n minus 1 times n minus 2. I won't forget my constant, a sub n, x minus c to the n minus 3. And I can continue going, and I'm going to take n derivatives. P sub n, and my symbol for n derivatives is n superscript in parentheses. So that's the nth derivative. Well, when we take our nth derivative, all of these constant terms, we're going to take enough derivatives that all of those constant terms go away, and my nth derivative is just going to be n times n minus 1 times n minus 2 times dot 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 times 2 times 1 times a sub n. All right. So now we're going to impose our requirements on these things. So we're going to say when x equals c. That's where we want our function value and all of our derivatives to agree. When x equals c, yes?
What happened to your x minus c on your nth derivative?
This one? Oh, we continue taking derivatives. So we started with x minus c to the n. If we take n derivatives, eventually we're going to have n to the first power, and then we take a derivative of x minus c to the first power, and then so that like the derivative of x to the first is just 1. So so we take enough derivatives that all of those x minus c's go away. When x equals c, we have p sub n of c is a 0. So when I plug in x equals c here, all of these terms evaluate to 0, and I just get a 0. P prime of c. When I plug in x equals c here, everything goes away except for the a1. And p double prime. Everything goes away except for the 2, a sub 2. And I go all the way out to dot 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 p sub n, the nth derivative at c is just n factorial times a sub n. And we said our function value and our polynomial values have to agree at all these points. So now we're going to say that, well, this is what our function, we were going to require that this is what our function values are at x equals c. So we want f of c and its derivatives to agree with p of c and its derivatives. So we're going to say that f of c has to equal a 0. F prime of c has to equal a1. F double prime of c has to equal, and I'm going to write this as up here, what, 2? I'm going to write that as 2 factorial a sub 2. And we keep going, continue, dot, 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 comma, and my nth derivative of f at c has to equal n factorial times a sub n. So that's our requirement for our function and polynomial. Well, this is how we're going to determine those a0, a1, a2, a3s, etc. Evaluate our function at our point, that's going to give us a0. Evaluate our derivative at our point, that's going to give us a1. Evaluate our second derivative at our point, divide by 2 factorial, that's going to give us a2. Evaluate our nth derivative, however many terms we want in our polynomial, divide by n factorial, and that's going to give us a sub n. And then we'll have our Taylor polynomial, and it's going to satisfy our requirements. All right, do we see the process? Yeah, it's pretty straightforward. We just make these requirements and then do the operations and see what that tells us about our constant terms there. All right, so now we're going to, motivated by this, we're going to define our Taylor polynomial, and we'll also define our Maclaurin polynomial when we expand about c equals 0. So we're going to say our nth Taylor and Maclaurin polynomials. And we need our function to have n derivatives. So we're going to say if f has n derivatives at c, then p sub n of x equals f of c plus f prime of c times x minus c plus f double prime at c over 2 factorial x minus c squared plus dot 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 plus our nth derivative f sub n, or f nth derivative of f at c, get a little more room here, times x minus c to the n over n factorial is our nth Taylor polynomial for f at c. And if we expand, yes?
Is that supposed to be f double prime, or does that say f prime?
Which one?
The second term.
This one?
Yeah, is that f double prime?
Yes, that's f double prime. And if c equals 0, so we're going to, if we expand about c equals 0, we say p sub n of x, we just have, instead of x minus c, we just have powers of x. F of 0 plus f prime of 0x plus f double prime at 0 over 2 factorial x squared plus dot 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 plus our nth derivative at 0 over n factorial x to the n. And this is our nth Maclaurin polynomial. So Maclaurin polynomial is just a Taylor polynomial expanded about c equals 0. It's nice when we can use a Maclaurin polynomial because you don't have these x minus c terms, you just have powers of x. And what we're going to want to do eventually is expand from a Taylor polynomial to a Taylor series. So we're going to do an infinite sum of terms, and then we're going to see when that series converges. And it's really nice when you can use a Maclaurin polynomial and your series converges for all x, because then things are nice and compact and easy to work with. And if you're a physicist, you might just say your function is a constant. For small x, that's what you would say. For small x, the function's approximately constant. All right, oh, speaking of physicists, by the way, did you see Hear the Nobel Prize for the detection of gravitational waves? That's pretty awesome. All right, so let's look at an example. Before I do an example, there are other kinds of series approximations that you will see in the future. One that is particularly useful and that I really like. So there are other kinds of approximations. One kind that shows up a lot in, well, you'll see it in physics when you study partial differential equations, which means you have derivatives of position, derivatives of time, so you have more than one kind of derivative involved, is called a Fourier series. And a Fourier series approximates a function with a series of just sines and cosines. So you have something like a sub 0 plus the sum n equals 1 to infinity of a sub n sine omega sub n x plus b sub n cosine omega sub n x. So you approximate a function with a sum, an infinite sum of sines and cosines with various frequencies and amplitudes. And the frequencies and amplitudes you find by requiring various things about this function.
What does that say?
What's that?
A sub n?
A sub n sine omega sub n x, b sub n cosine omega sub n x.
Which we need to know these.
No, I just wanted to say there are other kinds of series approximations other than Taylor polynomials. And what happens with Fourier series is, for example, if you wanted to model a square wave.
Wave of a square.
So you have just like a pulse of voltage that's constant for a while, and then it drops off, and then a pulse, and then it drops off. They call that a square wave. So the first term of your Fourier series might be just a sine or a cosine curve that's like that. The second term might be something with smaller amplitude that's like that. The third one might be another one with smaller amplitude and higher frequency like that. So you end up modeling the square wave with something that ends up looking kind of like this. And you just have sines and cosines. And sines and cosines are nice and easy to work with. You sum up enough of these with the appropriate amplitudes and frequencies, and you get really close to a square wave. So that's just another kind of approximation for functions using just sines and cosine functions. It's kind of a nice thing. And there's some properties of these series that make them easy to work with in certain situations. All right, so let's look at our example. So this is just one example of other kind of approximation other than a polynomial approximation. All right. So let's say we want the first four Taylor polynomials. So I'm going to look for P0, P1, P2, and P3 for f of x equals 1 over x centered at c equals 2. So we want to come up with a polynomial approximation for 1 over x. And we want to center it at 2. So the way I usually do this is I like to make a column. F of x is 1 over x, column of my function and its derivatives, and then I make a column of the function evaluated at my point. So my first approximation for 1 over x close to x equals 2 is 1/2. That's a pretty good approximation for 1 over x around x equals 2. F prime is minus 1 over x squared. And f prime of 2 is minus 1/4. F double prime is 2 over x to the third. F double prime of 2 is 2/8, which is 1/4. And we need our third derivative is negative 6 over x to the fourth. And f triple prime at 2 is negative 6/16, which is negative 3/8. So those are all of our coefficients that we need. So the first Taylor polynomial, P0, is just our function value. And if we were very, very close to x equals 2, 1/2 would be a pretty good approximation to 1 over x. P sub 1 is 1/2 minus, this is our coefficient, 1/4 x minus 2. P2 is 1/2, we have these two terms, minus 1/4 x minus 2 plus 1/4. And then we have a 1 over 2 factorial. So I'm going to put that there just to make it explicit, x minus 2 squared. And our third, we have these three, 1/2 minus 1/4 x minus 2 plus 1/16 x minus 2 squared, and then I'm going to do plus, or do we have a minus? Minus 3/8, and then I have 1 over 3 factorial x minus 2 to the third. And this comes out to be 1/16. So for x near 2, if we evaluate this, especially this third polynomial, we would have a very good approximation to 1 over x at that point. All right, so for example, if we wanted to approximate if we wanted to approximate 1 over 2.8, this would be pretty good. We could use this third Taylor polynomial, and we would get a decent approximation. But we could make a different choice. We could say, well, wait a minute. 2.8 is closer to 3 than to 2. So we could approximate 1 over 2.8 by constructing a Taylor polynomial centered at x equals 3. So we're 2.8. We say 2.8 is closer to 3 than 2. So let's approximate this with a different Taylor polynomial. So we could use a Maclaurin polynomial. For a better approximation. So we could expand, I'm going to go to the next page. We could expand f of x equals 1 over x plus 3 about c equals 0. And then we would approximate, then we would let x equal negative 0.2. We'd be a little closer. So if we did this, I'm not going to go through the process, we would see that our third Maclaurin polynomial here is 1/3. I'd go through the same process as I did before, take my derivatives, evaluate my derivatives at 0. We'd get 1/9 x plus 1/27 x squared minus 1/81 x to the third. For our third Maclaurin polynomial, expanded about of 1 over x plus 3, expanded about c equals 0. So to approximate 1 over 2.8, we let x be negative 0.2. So we're closer to our point when we let, we're closer to our point, our centering point, when we let x equal negative 0.2. So in this case, so for the Maclaurin polynomial, gives us, for this approximation, 1 over 2.8 is approximately 0.3571. And for the Taylor polynomial, gives 1 over 2.8 is approximately 0.3480. And my calculator says 0.35714. So this is a pretty, with 3 terms of this Maclaurin polynomial, that's a pretty good approximation. And your calculator is probably doing some kind of polynomial approximation for its calculations also. There's some kind of approximation that it's doing. Same thing for sines and cosines and tangents and all of those kinds of things. Now, what we're going to do, where we're moving, we want to make Taylor series. We want to make an infinite series of terms of polynomials. But we want to simplify our work a little bit. Because imagine doing this process, let me go back here, this process with something like inverse tangent. So you want a Taylor polynomial for inverse tangent, or secant x, something that involves really messy derivatives, or something like x squared times a quantity e to the x minus cosine x. So you want a polynomial approximation to that. Taking all these derivatives, evaluating all those derivatives, that's a lot of work. So what we're going to do as we move forward is we're going to find some ways to, one, we want to figure out when these infinite series are going to converge, but then we want to find easier ways to come up with them. And what we're going to do is do operations on power series, Taylor polynomials that we already know to get new ones. So we're going to differentiate power series. We're going to integrate power series. We're going to manipulate the terms of the power series to get new power series that we want. And we don't have to do this process of finding polynomials and then maybe having to figure out a pattern for the coefficient, for the nth coefficient, something that has to do with n factorial over n, 2n squared plus 1, something like that. So we want to bypass that difficult work to find our series. All right, questions? Taylor polynomials are very useful, very powerful, but the work to get these coefficients is kind of computationally not even necessarily intense, but kind of computationally tedious. Yeah, tedious. Yeah. All right, but what is it that I said had on there last week? The price of the price of clarity is complexity.
No.
Yeah.
No.
Sometimes the price of clarity is tedium. All right.